Hello again. So in this video, we're going to take another look at Pauling's rule number 2, but instead of using quartz, as we did in an earlier example, we're going to look at the mineral pyrope, Mg3Al2Si3O12. So this is the mineral pyrope, and it is part of the garnet group, or the garnet family of minerals. So the difference here is that when we looked at silica, we just had one cation to concern ourselves with. Here we have a whole host of cations, and again, these are all bonded to oxygen. So how would Pauling's second rule, the idea of electrostatic valence bond strength, apply to garnet? Let's clear the chalkboard and rewrite the mineral formula again. So Mg3Al2 Si3O12. And as we did with the quartz example in the other video, we need to figure out the coordination number for oxygen. We'll call it N. And for the case of magnesium, we know that it is 8. For aluminum, it is in 6-fold coordination. And for silicon, it is in 4-fold. So each magnesium is bonded to 8 oxygens, aluminum is bonded to 6 oxygens, and silicon to 4 each. So how can we determine N? Well, one of the ways we could do this is just separate the cations from the oxygens and then take a look at the number of atoms that are in each coordination state. So we have 3 atoms that are in 8-fold coordination, so we could take 8 times 3. Then we will add to that the number of atoms that are in 6-fold coordination multiplied by that coordination number, so 6 times 2, plus we have 3 atoms in 4-fold coordination, so we'll take 4 times 3. And then that will be equal to this product here, 12 times n. We have a coordination number of n that we want to find out, and there are 12 atoms that are in that coordination state. So this is 24 plus 12 plus another 12, and that is equal to 12n. N is equal to 4. So that means we can cross that out here and put a Roman numeral 4. So oxygen, on average, should be coordinated to 4 different cations. So what does that mean from the electrostatic valence bond strength principle? Let's erase the chalkboard and draw an oxygen atom. And that oxygen atom is going to have 1, 2, 3, 4 bonds emanating from it, just as we had determined in that previous slide. Now, what is it going to be bonded to? Well, we have magnesium, that has to be involved somehow, and silicon and aluminum. But now we've run out of cations. These are all the different kinds of cations that are in pyrope. What would go over here? Well, it could be another one of these atoms, and to find which one is most likely or most common, we can use the electrostatic valence bond strength idea from Linus Pauling. So let's take a look at magnesium. Magnesium being in 8-fold coordination and with a 2 plus charge, it's going to take that 2 plus charge and divide it amongst all 8 of those bonds. And that means for each bond, it's only going to have a quarter charge that it can donate total for each bond. So for aluminum, same idea. It's in 6-fold coordination, but it has a 3 plus charge. So 3 plus charge divided 6 ways means there is only a half a positive charge per bond. And then silica in 4-fold coordination, it's got a 4 plus charge. Divide that amongst 4 bonds, and then each bond will get a +1 charge. So for silicon, we've got a +1. Magnesium, each bond gets a quarter charge, and then for aluminum, each charge gets a +1/2. For the case of the oxygen atom, as usual, it has a 2 minus charge. So now we can take a look at what might fit over here. So we've got a +1 coming from the silicon, +1/4 from the magnesium, and a +1/2 from the aluminum. Those all sum to a little bit less than 2. Those are not going to completely satisfy this -2 on the oxygen, But what if we put a magnesium over here and we add a +1/4? Well, then all of a sudden, all 4 of these will now have a positive charge of +2 that now matches the negative charge on the anion. So in this case, we would say that magnesium is the most likely fellow to be put into this slot. Now, there are other kinds of atoms that could fit into the structure. So one of the neat ways of thinking about Pauling's second rule is we might ask what other kinds of atoms would work. Well, anything that has a 2+ charge that is an 8-fold coordination should be able to substitute on that site. So we could start playing games with thinking about other kinds of atoms that might fit based on a radius ratio analysis that we looked at in an earlier video, and then asking whether it would be stable in terms of the electrostatic valence bond strength and whether or not the positive bonds that reach the anion completely match the negative charge on the anion. And when they do, that would be, in a Pauling's rule sense, the most stable state, the lowest energy state, and the one that would be then most likely. It doesn't mean that magnesium is the only option here, or that you can only put 2+ cations there, but that they would be predicted to be the most stable and the lowest energy state.